Okay, don't follow the title because the title is too generic. It just was okay. I like to start. There is a short video presentation of that I gave a recent conference just to present my book that is just coming in a few weeks. That is just on this problem, in the problem of explaining that everything you can think, your mind can think, is already hardwired into rational numbers. And so, think about Paul Dirac spent his own life trying to find a better representation of the quantum mechanics modeling, and then everything is already hardwired into rational numbers. But we have to learn the way to unfold the kind of waveforms.
Some kind of itself that most of the time.
The audio is the maximum that I can do.
And that's the reason I said
Can you say it in words? I mean, you know what you're saying, read your lips.
Yeah, but you know that sometimes words are just in the right sequence in a short time to be presented.
we don't need that, but they use it. That's the usual way academic knowledge goes. I just understand that I realized that all of these things were just tools from the scientific community and mathematical approach. We are just inside rational numbers, but just in a good way. So the starting point from the book was just the awareness that it's up to us to decide which path we like to get most without just forgetting the complementary path that we have when we split something. And that's something that we have to be aware of, because any time we split something, we lose it. And from the point of view, quantum theory was quite effective, but not in the usual sense that you can achieve and so, I like the real things that I like to experience in real life. And so I discovered that anything you can talk, anything your mind can think, is already applied into rational numbers. It's just up to you to be able to unfold that information, just to realize that you are using just something that already shared right with you without and so his answer was, I don't want to. And then it took about 6 or 7 years of research to realize by myself that as a matter of fact, he was the answer. And so I had to find out the data by myself. And that's it. And then I was able to distinguish random noise from the deterministic noise. And as a matter of fact, again, everything is already coded into rational numbers. It's up to us to be able to unfold that kind of information. Use that in useful way. I think that it's a fantastic opportunity for mankind just to grow, to be ready.
Okay, so for me, that I focused on solving real problems. The major the system in a strong way, is just to be able to discriminate the random noise that you can get from experimental measurement, from the deterministic noise you can get from the measurement. Because even yesterday we were told that anytime we get a measurement in an experimental environment, then we get noise associated to our measurement, and then noise is always random. But it can be proved even mathematically that pure random noise is not, is just a mathematical abstraction. At a real level, there is no completely random noise. Any random noise, observed random noise, inside has a structure that is concealed by other structures that are really a summation, the resultant of many different components that we are able to unfold, and then we are forced to accept as something that we are unable to figure out, and so we call that noise. Okay, this is just for discussion. For instance, if you want to discover something new, you need to be aware that any time you see something and you get information, usually you represent that kind of information, your brain represents that kind of information in a way that you are already expecting to see. For instance, if I present you this figure, I ask you, what is this?
Not cycling.
Huh?
Cycling.
Cycling. Yeah. And in fact, because that's the result, because we are expecting a picture to be arranged in a specific way for orientation that our brain is just expecting to receive.
What did he say it is? What did he say?
Well, a cycling path or something.
Oh, nice cycling path.
Yes.
That's what I think you need when it's
Exactly. And then if I do this kind of thing, just
No, I mean,
180-degree rotation. Now what is this?
Colorado River. No, Grand Canyon está en Arizona.
Colorado River, Utah.
It's in Utah.
Yeah, the part in Utah because it travels.
Okay.
So, just to give you an example, the way we have to be aware of the processing of our brain that is already formatted. I mean, and when you grow, you learn to receive information in a specific way. And so, if you are expecting the kind of information any time, then you force yourself to be able to unable to discover the things. And so, it is fundamental to understand the difference between unperceivable and measurable. For instance, I'm pretty sure that you experience something that is perceivable but is unmeasurable. Think about your intuitive side, your intuitions. You perceive your intuition, but they, right now, cannot be measured. And then something else that can be measured but cannot be perceived. I give you immediately an example. This one. This is a random image, full color image, okay? The one you can get from your camera, from your phone, something like that. And so I ask you, this is a random image, so you see there is the usual computation of the channel entropy associated with the image with simple precision, double precision, quadruple precision, just to be sure that the numbers don't trick me. You know, just if I truncate the operational result. And that's something that, I mean, you can perceive randomness there, but you are unable to measure. And in fact, if I get a second image, and I ask you which one of them is more random, okay, you cannot perceive the difference. Are you able to perceive that difference? So it's something that we are not able to perceive, but we are able to measure with specific tools like channel entropy. And in fact, you see down the computational channel entropy of the second image, and the bottom image, according to channel theory, must be more random than the upper one, because it's closest to 1. You know, because the channel entropy varies from 0 to 1. The closer to 1, the more random is your image. Then the information content of your image. Well, I tell you, unfortunately, that is the correct channel entropy computation, but it doesn't match reality, because the bottom image is completely deterministic. Completely deterministic. In fact, the final test, which one of them can be compressed most? I mean, you see, the bottom one can be compressed around 314 times, and the top one cannot be compressed because it's the real random one.
So it's compressed by GZ, by something?
By a known structure. You know? And so, just to give you, and this is the example that started my research, I found the answer that I was asking to Benoit Mandelbrot at that time. Because in this way, I am able to make a discrimination between pseudo-random noise and deterministic noise. Even if we are unable to do that, even if our machines are unable, current machines, current experimental machines, current instrumentation machines, even sophisticated ones like the ones in CERN of Geneva, are unable to do, because they use only traditional numbers. Okay? Just a little example. But if you go to specific application, okay, then we can develop predictive, more advanced predictive competence, numerical competence, but the point that I need to show you is that, okay, this is the fundamental relationship that if you start from discrete starting point and going up, relates rational numbers going left to right, though they similar representation going right to left, and then if you start from left to right or right to left, sooner or later you arrive to a oscillating sequence. A repeating, a cyclic sequence. And that cyclic sequence is just the sequence that you get as a representation on 1/d. As I said this morning to Professor Acampo, for instance, if you take the Fibonacci sequence, then the Fibonacci sequence is divided into 1/89. And I can give you the relationship for any number you like. Okay? But jump immediately to the recurrent sequence that is able to give you the correspondence with a specific, a unique rational number. So, a one-to-one correspondence. And this is just one, there are four that are fundamental one, but this is just the master one. And you can relate this kind of approach immediately with the domain of the C transform, and in fact you see there all the possible solution, but according to the traditional control theory approach, they focused on the unity square, a unity circle, and they were interested only on stability and instability of systems, in the sense that if your poles, the poles of your equation are inside the circle, your system is stable. If they are outside, your system is unstable. And then you can transform the domain of the Z transform with the trusting transformation to the usual domain of the Laplace transform immediately. And so you recover all the classical solution of the complex plane. So, rational numbers are able to encode complex information, complex plane information in a very efficient way. And then this is something for me fundamental, because if we want really model the system in the right way, capturing as much as information we can, we have to focus on this kind of diagram. In the sense that think about we have a problem to solve, so we focus our attention on the problem to solve, and that is the system in the middle. But if we focus that information, that problem only, and we don't build a resilient conceptual framework like that one at different levels, then we are completely unable to see all the relationships that our system can have within its environment. And specifically, we completely miss this component, this one and this other one. And that's a major problem for current modeling, system modeling in physics. They don't take into consideration these components at all. And then, okay, so our modeling system, our modeling approaches have only a limited window of application, of predictivity. And so we need, this is just a resilience conceptual framework that gives you the possibility to choose from a top-down point of view approach, the one I anticipated to you, the classical traditional one, analytical approach. That is, you start from top, you go down, but as you go, much noise you get. That's typical when you try to go to nanoscale level, that the signal that you want to acquire is completely immersed into noise. And you are able to discriminate signal from noise. Or you can start from bottom, going up, and then you think that you solved your problem. That's not the case, because you go into combinatorial explosion. And so you can use a more powerful machine, but then you need a new ceiling, a never-ending story. And then in that sense, we will get anyway a gray area to describe our modeling that is not really strong by a modeling point of view, because our information content will be corrupted by noise. The fundamental reason is this one. When we focus on our problem, we describe our problem on a direct space that usually is a Euclidean space only. And we completely forget that there are other components if you want to fully conserve our information content. And those other are the codial space, the reciprocal space, and the reciprocal space. We don't even think about those ones. And we don't even think about the relationships that we can get from those four components that are just, unknown, because don't even think to search for them, and even less the cross correlation between the reciprocal space and codial space, and the reciprocal space and codial space. And then if you want to be more precise by mathematical point of view, think codial space as the identity transformation, the codial space as the additive complement to the direct space, the reciprocal space as the multiplicative complement to the direct space, and the reciprocal cospace as the dual to the direct space. The dual that you get combining codial space and reciprocal space. Only in this way we will be able to conserve the full information content of our reality, or our specific problem to solve.
You have dimension?
Any dimension you like, because it's self-scalable. That's the beauty of this approach. And in fact, okay, we go into details of the modeling, but I see that. But the fundamental things that we have to realize that usually when we model something, we have a natural system, then we have an encoding by experts, and then we have a formal system. And then we have just a knowledge base we use to solve, to represent in a correct way. And then we have decoding in some perturb the system to obtain the final result we like. But unfortunately, we formally encode only this part, and we completely forgot the encoding part, and then just the representation part of the art, that are the forming information formal interface to the natural system. You can map immediately this approach to our body.
Is this Rosen, the Rosen?
Exactly, this is Robert Rosen modeling approach, but then on my ODR proposal.
Any relation with anticipation?
Yes, well, I don't have here but if you express everything with recursive expressions, then, for instance, you already saw in some book, if you have let's say that the most known second order recursive relation is the Fibonacci relation. If you explicit the Fibonacci relation at any time, at any point of the Fibonacci relation, you are able to anticipate all the other values you like in the sequence. And so, if you are able to do that for Fibonacci, I already told you that the SIB approach is already hardwired into all the other rational numbers, then you are able to anticipate all the trajectories that your problem is presenting you. You're able to select in real time, even in real time, the one that will force the system to get the result that you like, or not if you have not enough resources, but you will know that in advance. And that is the major point. That is, if we use the ODR approach, then we have to be aware that we have to gather information of the codirect space if we want to just gather the major information content for our problem. Okay, I have no time to show you all the details. But this kind of approach, for instance, is fantastic to model. I just mind because this morning we got an interesting example of conflicting representation systems that can be modeled exactly by this approach. Because we started from an action domain, experimental, where the experimental observation quality as personal level, but we have to transform the information that we gather at this personal point through a formal system that allows us to arrive at a description level that allows us to communicate in the right way. But if you use different formal systems to format our subjective experience, then we will be unable to share any description and we have conflicts. And then let's assume that we're able to share this kind of experiences with a final decision that we have to decide in advance before starting to talk. If we want to just avoid wasting time, then we can have the maximum information transfer, but a final precision only. Then anybody that participates at the talk we have an opportunity, according to his past experiences, knowledge base, anything personal, to build again a representation at higher precision level, using all these kind of resources at personal level. And we call that learning. If you start recurring with this code, that space, then you are able to grow much faster than the past, your knowledge base. So this is the other channel, observation, description, representation, and this is the ODR domain associated with that. We need both of them to conserve the full information. And then we'll be able to solve the problem of the multi-scale system modeling, because in this case we'll be able to avoid the kind of problem I showed you before. And we started with a representation, a solution that is centered on the system that we are interested in, and from that growing and amplifying the solution with as less noise as possible. And so now we have an option for modeling. We can go with the classical way that can be convenient for specific problems, that is up-plane space, for instance, and then we can use that for inner matrix operational representation compromise, and representation space, all the properties that I think you already know from the Poincaré half-plane approach. But then now we have the OECS space with all these new properties, really matter as a representation operational compromise, and another representation space, one more equal to its inner representation space. Think about the brain mapping of your reality, and then natural system dynamics framework, the quantum theory approach, to model projective relativistic geometry and to anticipate emergent system dynamics, and then the observer can become a system natural co-artifacts. And with the previous approach, the spectator can become a system in natural perturbation, by definition. And so we are ready to jump from quantum to qualia. So the quantum jump I am referring to is a jump from quantum to qualia, from inner matter to living organisms. Okay, but now, if you like it, I can give you just a very example. Going down to each component, if you are passionate. Otherwise, you like. It's up to you. I don't want to just force you to follow it. But I felt necessary to give you this kind of presentation to give you an overview of the problem I tried to solve. And then, but this is just an overall scenario. If you want more specific solution, I can give you an example where you can match the discrete approach with the analytical one with no information dissipation. It's up to you at any level, even doing computation and anything you like. So, what is your feedback? Answer. It's late, you are tired, it was a long day, maybe some other opportunity.
I'm sorry, is there any medical usage of this?
Oh yes, absolutely. If you like, I can give you an immediate example that I presented at St. Petersburg recently for image compression. Okay? But this is just a little example, because there are so many. Excuse me?
Everybody's fine talking.
Yeah, sure. Okay. What can I do? You want to see the design?
Can I suggest please to please show the example?
Yes. Okay, I skip all the rest, I go immediately to the point. This is just to give you an idea, just a little excerpt of the discrete Riemannian space that you can build with this approach. And then you can even define operators, vertical and horizontal operator to move into this space. For instance, in this way, you see going upscale and downscale. And then something maybe for you, because you probably already heard about prime numbers, hopefully. But nobody told you before that, as a matter of fact, prime numbers can be arranged into different families with different properties. And this example is So solid numbers are prime numbers, but prime numbers cannot be solid, okay? Because there are many different families with different properties. We refer to this family because the first one has a specific property. Every period of any number related to this family, prime number related, has an even period. And even period has specific properties. Reality is even. Our reality is even. And I show you that going to numbers. Okay, this is number 1/7. Okay, 1/7. Here you have the quotient digit of the first two periods. You see, 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, and then the string of the related reminders: 3, 2, 6, 4, 5, 1, 3, 2, 6, 4, 5, 1. Okay, and those are just the index that you have to use to index those digits, the position of those digits. If you go left to right, or if you go right to left, because in this way the system that you create is completely reversible, so conserving information, no dissipation at all. And so this is the graphical representation of the reminders here. You see, you get some kind of wave, okay, but it's strange. It's not the way we are taught from analysis, because we are accustomed to this sinusoidal waves, you know, sinusoidal waves. Yes, it's a discrete wave, but has a fantastic property. I show you immediately. Now, okay, the same way. Now, you see at A and B, I told you that all these waves are even, so I can be divided enough here, and now I can compute the complement, the additive complement of this part, and the result is this. So you see, inside the period of rational numbers, of solid numbers, you have direct space and codirect space component together. You have the full information content of your outer universal representation. This is really amazing. And then you can even discover that 1/7 can give you this kind of grouping of information. You know that the final plane is just the most elementary projective plane you can get from geometry. And 1/13 has two coupled final planes coupled inside, divided inside. And then we go further to 17. 17 is another solid number, but has a further interesting property for you. You see 4 part A, B, C, D. You already know that if we split this one is the complement, the additive complement of the first one. But now, if you map that with the Fourier transform of this guy, you see this is just to be sure that I tell you the truth. You see the additive complement there. Then you get this kind of thing. Think about it. You have all the component of a rotor, of a rotation, already come inside 1/17. Okay, 1/17 is the first solid number that presents this property. And so on, okay? It's a never-ending story, because that's the reason I tell you everything we can think about and everything we can not even thought about is already a international number. It depends only on how far you want to go in with number system, with integers, you know, or even better, natural numbers, because we are talking about numbers. And this is the fundamental relationship that relates to this 1/7 components with the usual solution that you get from analysis as rules of unity. And so you are able to get all the interface generators and relations, either from reminders, from quotients, and outside, and analytic And they are just there for everybody. So it's not just up to you to be able to use this kind of information to develop smarter algorithms, smarter simulation systems, and so on. And just to give you an explanation for the compression algorithm that I used to make a comparison with the most powerful compression algorithm we have on the market today, then like JPEG or some more advanced than those ones, they use just advanced knowledge to be able to compress information in a major way. I show you that our approach uses zero knowledge, and we are able to get even better results than those ones. And as only 6 members of the family, think about a large number where you have billions of family members. You need just to compute the first one to know the result of all the others. And so, for instance, in this simple case, think about, we want to know, we compute 1/7, so the first line in the top, and we ask to compute, for instance, any other member of this family. Tell me from 1 to 6, because it's a small family, please. Any number? 1, no, 1 we already know. I mean, that's the identity, the fundamental identity. What?
You said from 1 to 6?
Yeah, because we have only 6 members of this family. So, anybody?
Doesn't matter. You say it's 4.
4. Okay, so from the first line here, you see we find 4 as a reminder. Our 4 is 4. Now I go immediately to Q5 to the following one as a function. And then I have 5, 7, 1, 4, 2, 8. 5, 7, 4 over 7, 5, 7, 1, 4, 2, 8. Already there. I don't need computation a lot anymore. Just a point and play inside my computer machine. And so I can save a lot of computation, a lot of time. And in fact, we try this kind of approach. Okay, this is the
Now, is this the type of answer you were expecting?
No?
Okay, no.
No, this is just to explain the algorithm. And then the final result is the one.
I think you have abilities to
Yes, but it's just a one slide. Okay? Comparison with different commercial packages.
Because I don't know what this has to do with. I don't see the medicine anywhere. Well, I don't know. It seems to me as if this is concerned with not specifically medicine, but with anything. So I don't see the medical part of this.
The relation that you get on the reminders are just a relationship that you can get from a higher point of view with the same symmetries that you're looking for. That is instant.
It is a matter of algorithms, but I think you want something more specific to medical. No?
Yeah, for instance, this is just an example of even if we mentioned that this is the compression, and then we made just a comparison with different images with different compression packages. Okay, this is the benchmark, just is the description, the information from the images, and this is the definition of the KPI index to measure the frequency between images, and this is the final result. You see here we have our algorithm, and those are the other ones, and you see that the only image that is not competitive with our algorithm is this one. Why? Well, we went to the village and we discovered that there was an image with a lot of linear details that our algorithms were already pre-programmed to take advantage of. Our algorithm is zero knowledge algorithm. So those are the only images where our algorithm is unable to perform better than all the others. But the reason is quite simple, because they are pre-programmed to take advantage of the linear components. Our is not, because it's general, it's universal. And in all other cases, it outperforms all the other compression algorithms. Okay, just to show you that we started using in a practical way this kind of information and disclose it. And the major property of this algorithm and all this approach is the larger the information you have to manage, the more compressing capability of this algorithm. And it's just the opposite of all the others that you can find on the market. And it goes up quite fast. Okay, thank you for your attention.